All right, good morning. Happy Thursday. Last Thursday class, because next week we won't have class on Thursday. So Monday we have chapter 25, which is just a very brief look at amino acids and peptides and proteins. And you won't be expected, obviously, to memorize any amino acid structures, just to be able to do some reactions with those and then figure out what their protonation status is at different pHs. And then Tuesday, Wednesday will be review. We have a week homework 5 that is set up to be turned in for next Monday, and then your retrosynthesis is due on Saturday. I think that Saturday, or I keep Saturday. Yep. And then today opens the quiz, and you have until tomorrow to complete the quiz. Any announcements or questions on what's going on the next week? Okay, so let's just jump into our synthesis problems here. So I know some of you asked for this ahead of time. If you have any suggestions or questions or how to dissect these things, you can ask them in the chat, or you can chime in with audio. I think there's only 2 of you in class right now. You are free to jump in, but I'll just kind of, I didn't have any student answers on this one. The next couple problems I do, but we can look at this one. So one of the things that I look at here, there are different things added, but I want to find my original carbon chain, and that is right here. So there's my original carbon chain, and I can see that if I kind of go back one step, I might have had the carbonyl still there. Once you have that carbonyl in there, you can look to what could have happened. And what I noticed is that this carbon here, where that CN chain is added, is at an alpha carbon. So I might want to do some alpha carbonyl chemistry there. So if, and then the amine could have been made using an acid chloride or something like that, or the amide here before it was reduced. So we have an alpha carbon chemistry. So you might have had this, or we might have had whatever carbonyl there before. So if this was alpha carbon chemistry, we could do that with the aldehyde. And the CN, some of these things that we've seen here, this is the new bond being broken. So that might have come from the aldehyde plus this Michael acceptor. All right, so if I start with the aldehyde, if I want to do a Michael addition, which this is over here, I would either need a dicarbonyl or to use the storic enamine. So I'm just going to add diethylamine with an H plus catalyst. And then I'll add the nitrile to that. Work that up with water. So at the alpha carbon, I get my new bond. So that will add the nitrile part. This was 1, 2 carbons to the nitrile, 1, 2. And then for the amine, this is a secondary amine. So you could go through an acid chloride and then do a reduction if you wanted. But the efficient thing to do here is to do our reductive amination. So you can just take isopropylamine with sodium borohydride or sodium cyanoborohydride. And that would get you your target molecule. Any questions there? So there might have been maybe more lengthy. So if you had gone through the acid chloride, you could hydrolyze that to the carboxylic acid, the aldehyde here. Use SOCl2. And then excess amine. And then you'd have to, you might encounter a problem here with using lithium aluminum hydride because that could also reduce the nitrile. So you might not want to take that one. And I don't know that we have, you might be able to use, not this one. Yeah, I'm not sure what, I don't think we have a reagent that will do the amide that won't also do the nitrile. So this might not be the best route. I think your reductive amination is your best bet here. Questions there? All right, so this is the next synthesis. And let's see, this is something that a student submitted, and we can kind of go through the different steps here. So the first step that the student did, so in this reaction here, we're adding the fluorine and this whole host of other groups here. And you can't just add this whole thing with an AlCl3. You're going to have to do a couple of other reactions. So we'll see what the student did here, and then we can figure out a way to fix the synthesis. All right, so I believe on this particular problem, the students were allowed to use reagents with one functional group, and I might have had a 6-carbon limit on the synthesis, so you couldn't use something with more than 2 functional groups. So on the first reaction here, there's already the use of 2 functional groups. So you would not be able to use that reagent. So that student lost points there. But let's say they, we'll just keep going. So assuming that this reaction could be done, they then used HNO3, which does go meta to the carbonyl group that's there. And then they use HBrROOR to add the bromine to the end of this molecule right there. So that reaction works. Then they use magnesium to make a Grignard from that bromine. The problem with adding a Grignard here is that you also have a carbonyl in the present, so the Grignard can react with another molecule of itself. So we don't want to do that. And then assuming that, let's say the Grignard did work or they protected the carbonyl, let's say you can protect the carbonyl and then make that Grignard, and then they used LDA to attack at this position here. Again, this molecule's got 2 functional groups. It's kind of cheating there. But let's say that one did work. You wouldn't need LDA because your Grignard is already nucleophilic. And then they did the zinc HCl to reduce the amine, which that is okay. And then they used HONO and then to convert it to the N2 and then added the fluorine there. So overall, I mean, there's parts of this synthesis that work okay, and then other parts that don't work as much. But the big ones were the first step there with the functional groups, and then your Grignard is going to be the problematic steps. So things that you can do instead of that is, again, you'll notice that you have the fluorine. So that was a good thing to recognize that that needs to come from an N2. I'm just going to put R here. So we need an N2 in order to do that, which means we need to have the nitro group. And then if I look at the other molecule, I can easily add this via the Friedel-Crafts. And then what I'm noticing is that the functional group, or this cyclohexanone that's getting added, is on the alpha carbon. So I can do some alpha carbonyl chemistry. This is a 1,5-dicarbonyl, which makes me think of a conjugate addition or a Michael addition. So if I'm kind of dissecting that part, I have this plus that one there. I suppose that one has two functional groups, but that one is a fluid functional group. It's an alpha beta unsaturated carbonyl versus an alkene and a carbonyl. Okay, so our pieces that we need to make is we need to add the nitro group, and then we need to add the benzene or the acyl group here with that benzene ring. So in the forward direction, we're going to do our Friedel-Crafts to add the carbons first, because if we add the nitro group first, we won't be able to do the Friedel-Crafts reaction. So I'm going to add the 3 carbons. And then this is a meta director because it's electron withdrawing. And that's what I want, is that meta to there. So I'm going to add the nitro group. And then with the nitro group there, I don't want to reduce my carbonyl because I need that as a carbonyl, but I can reduce the amine or the nitro group without having it have any other effects there. And so I'm going to use iron and HCl in order to reduce that. And then you can go to the steps to make it the fluorine. So we'll use NaNO2 and then HbF4. And you can do that later if you wanted as well. I'm just going to do that now. And then for the alpha carbonyl chemistry, I want to do the alpha addition at the alpha position and make it into a Michael donor. So I'm going to go through the storic enamine again because I don't have a dicarbonyl. And then I'll add cyclohexanone to that and work it up with water. And by doing that, I'm going to do 1,4 addition right there. To get the target molecule. So if you didn't use a storic enamine, so that secondary amine there, you could risk the possibility of the enolate adding at the 2 position. So it could add at the carbonyl carbon instead of at the 4 position. So that's why we use the storic enamine. Questions there? All right, you can take a look at the next problem if you're not still writing stuff down there. Okay, so in this problem, we have nitrobenzene, and we need to get to adding a bromine, phenol, and a carbonyl. I have two actually student answers for this one, so we can just kind of pick apart what's going on here. The first one, there is that we start with nitrobenzene and add Br and heat. And we can't use Br and heat to add bromine to benzene. We need to use that iron catalyst. So that's going to be something we want to fix here is FeBr3. So if we fix that, then we get the bromine with the nitro group that's meta. And then they're adding AlCl3. So I see that they're wanting to do a Friedel-Crafts. We forgot the chlorine here, but really this reaction should be done first. Actually, we can't do it first because there's already nitrobenzene there. So we may have to, we'll have to add this later. Because we can't do the Friedel-Crafts with the nitro group. They did zinc chloride, so let's assume that this product was made, what they have there after the Friedel-Crafts. They use zinc to reduce the nitro group, and then use NaNO2 to make the N2, which has the plus there, and then use water and heat to make the phenol. So so that one, there's a couple of things that don't quite work there. And then with this particular student, they did nitro, added the bromine with the proper way. We have zinc HCl to reduce the nitrogen. That's fine. And then again, they're trying to do this Friedel-Crafts reaction with the nitrogen, the amine. This one also you can't do. Okay, so no Friedel-Crafts with the NH2, and then they used the NaNO2 and water. So the way that we can fix that NH2 reaction is we can deactivate that. So what you can do is add acetic anhydride. And then this is deactivating that so it's not so strongly electron donating. Do the Friedel-Crafts reaction. And that will direct it para, which is what we want it to do. And then once you've added the acyl group there, then we can just use water and acid to remove that acetate group. So that's one thing that we can do to fix that reaction. So the question is, do these steps need to be in a specific order? Because when I tried it, I did it similar, just in a different order. I think it will depend on the steps and what you did. So some steps don't have to be in the same order. So if you wanted to add your, let's see, let me think. If you reduce the nitrogen first, that is the one driving the bus. So if you, let's say that you did, let's say you reduce this to the amine, and then you wanted to add the bromine or the acyl group, let's say you acetylated that, this is going to be an ortho-para director. So your bromine is going to go to the wrong spot as opposed to putting it on first. So that bromine you probably want to add first before you reduce the amine. So I think it will depend. Some steps do need to be in a specific order. Sometimes they don't have to be. So that's really dependent on the rest of your molecule. So I'd have to see that what you did in order to judge if it's in the right order or not. And if you wanted to send me something to look at, I can look at that. Other questions on this problem? So the second approach was a pretty good one. We just had to add a couple of steps in order to fix that. So we don't want to do Friedel-Crafts with that NH2 there. We just have to deactivate it, and then the rest of the synthesis was okay. All right, so here is the next synthesis, and I have, whoops, a student one here. What this student did was they took the thalidomide. So this is the beginning of the Gabriel synthesis. Hopefully you recognize that. So this is the Gabriel. And we're adding KOH. And the goal of this, so this nitrogen here is this one right here. So we're starting with one nitrogen. We have to add 3 different groups to that nitrogen. And this one, the order here is less important, but we can see here they add KOH, which is the first reagent for the Gabriel synthesis. They're adding 1, 2, 3, 4 carbons, which is this 4-carbon chain over here. They were just mixing the NH2, which is needed to release the nitrogen. And then once you have that, you now have an N with 1, 2, 3, 4 carbons. And it looks like they added acetaldehyde for these 2 carbons right here. So that was this reagent plus sodium cyanoborohydride, which would give you the N. This would be N-ethyl butylamine, if you were naming that. And then for the final addition of the cyclohexyl group, they're doing another reductive amination, and it looks like it got cut off, but there is a carbonyl there. So that's what's cyclohexanone. So this was a much shorter synthesis than the previous one, but you have the N there that will do the reductive amination. So you'd have to do that 2 extra times to get the tertiary amine on that one. Questions there? And I'm sorry, go ahead.
Do you mind?
Yep. Let's see, if you had a question, go ahead and chime in. I was going to say the order for this one is not as important. So let's say you had the N and you wanted to add the cyclohexylamine first. You could do that, and then so the order of the N groups don't matter as much. When I'm doing it, I tend to use the bulkier groups first, just steric-wise, but it doesn't really matter which groups you added first. So in this one, the order is not as important in which you add the R groups. Other questions there? All right, this one we have a carbonyl, and I have, this is butanal. So if I try to find butanal in the other starting material here, it's right there. So I'm looking at maybe a reductive amination. And then it looks like I have some stuff going on at carbon 2. This might be some alpha carbonyl chemistry. So this is what a student started with. And so she wanted to do the reductive amination first. And then a carbonyl magically appeared. So there's a question mark there. So he or she was not really sure where they were going with that. But they did have some things that could be useful here. So this MCPBA step is good as long as you can make this alkene. But the problem with doing alkene, this would be trying to do some alpha carbonyl chemistry. But once you do the amine part first, you lose that alpha carbonyl or that carbonyl. So we don't want to do the amination first. And they used a Wittig here. So this reaction works with the Wittig. However, you have to get that carbonyl there first, which would be problematic. So this one is not the best route. Okay, so I mentioned I want to do alpha carbonyl chemistry, so we'll do that part first. And if I just do a quick retro from this one with the alpha carbonyl, so let's say I had this, and before there was this to make that epoxide. And somewhere between this aldehyde, I made the reductive amination there. So you can do that with the amine. And then before this, you would have just this one here. So this is an alpha carbonyl. And if you remember, you could either use LDA with something here, but this is an aldol reaction where you're doing this reaction at the alpha carbonyl chemistry. So you pull those two pieces apart and you can just use sodium hydroxide with cyclopentanone. So I pull that apart and put an oxygen on that second one, where that carbon double bond is. And that would give you this right here. And then at this point, we can make our epoxide, or we can do the reductive amination. The order in which we do those does not matter right now. So if you wanted to do the epoxide, you could do that. So you have your epoxide. And then for the last part, we're just doing a reductive amination. So the N plus whatever is attached to M. So isopropylamine with sodium cyanoborohydride. And that will get you the target molecule. If you at this point wanted to do the reductive amination, you could do that. And then do your epoxide to get to the target molecule. Questions on that one? So in that case, the first thing that you want to do is do the enolate or do your aldol reaction. And then after that, the order doesn't matter as much. Okay, so this one is not a traditional approach, but the student was pretty creative here. We start with cyclohexanone, and they did LDA and then alkylated with that cyclopentane and CH2Br. The problem with this synthesis here, though, is this step where they use Br2. And that is because Br2 and FeBr3, these are reactions only for benzene. It's the same thing with the Friedel-Crafts reaction. That only works with benzene as well. So you can't do Friedel-Crafts on cyclohexanone. Okay, but let's assume that you could get Br2 to those positions. What this student did next was add the protecting group to protect the carbonyl. And then they added Grignard to the Br, and they use excess so that this Grignard, although Grignard is an MgBr, so they just reacted it with both of those Br groups and then deprotected the carbonyl. So I would say this is creative, and they just got dinged here for the Br2 excess, and maybe they left off the Br here. So that is a creative approach, assuming that you could get this di-Br made. We do have ways to make the Br on that side if you wanted to do that using, I think, Br2 and H+, right? But this is definitely involving alpha carbonyl chemistry. So we have an alkyl group over here. We have an alkyl group over here, and then one that is added at the 4 position. In order to add a group at the 4 position, you would need to have a double bond here. So we need to somehow create that double bond. So the first thing that you can do here is to add the one alkyl group using LDA, and then the ethyl bromide. Or you could have added the cyclopentyl group there if you wanted as well. But when you do this, you want to make sure to use LDA again, because that will grab a hydrogen from the less substituted side. If you use sodium hydride, that would take a proton from the group that has the ethyl on there. Oops. Actually, you know what? I'm going to go back here. Sorry. Maybe I will add my cyclopentyl group first. Okay, so I'll tell you the problem that I'm running into here, because I haven't looked at this in a while. The problem is that if you saw the intermediate that I had before I erased everything, was I had an R group here and the ethyl group here. If you add Br2 and pyridine to make that alpha beta unsaturated carbonyl, you run into a selectivity problem. So it could actually do the BR at either side. So that's where I'm running into issues right now. But I think if I actually do the alpha beta unsaturated carbonyl first, that's probably the best way to go. All right, so we'll start over here. BR2, sorry about that. It's just me. Again, I haven't looked at this in a while, and this could be good or more confusing for you. Hopefully it's helpful, if nothing else. Okay, so BR2 plus H plus, followed by pyridine, is going to give us this double bond here. And then in order to add the group at 4, I want to use the Gilman or that cuprate reagent. And then that would just be the 2 ethyl groups with copper lithium, followed by water. And that will add the ethyl group, and my carbonyl is still intact. And then you can use your LDA. I suppose you can't completely control which side this goes to. So theoretically, it could go to either side here, but now we can use LDA again. And the cyclopentyl. Bromine there. All right, questions there? All right, so now, because I've forgotten, I looked back at our reaction book here, and the Br2H plus does go to the more substituted side. So if you had added the cyclopentyl bromine first, and then did the Br2H plus, that would have been okay. So this step is okay. Then you could add the 4 and then not have to deal with this potential here, the potential mixture at this step. That would have been very minor deduction though. All right, Barry, questions there before we go to the next problem? All right, I think at this point I'm out of student solutions, so this will be just a couple of problems here. We have bromine, and we need to add a carbon, or this whole group over here. So this could have come from an aldehyde plus this via a reductive amination. So I'd have to try to add a carbon from the aldehyde. It could also have come from an amide, which would come from the acid chloride. And I don't think you had to make the amine from ammonia in this particular problem. The quickest synthesis, I think, is to go through the acid chloride. And what I'm thinking of doing is making a Grignard, reacting it with CO2 to add the 1 carbon, which will give us the carboxylic acid. Then we can do the acid chloride. React it with excess amine. And then use lithium aluminum hydride. Questions on that one? All right, this one we have an OH and a Br. The 2 ways that we know how to make phenol come from a Br, which usually needs an electron withdrawing group, ortho or para. The other way is through the N2. Route, which I think would be easier to get to than this di meta Br. Also because Br is an ortho para director, the other one is meta. So I think I'll go through the azo compound there. So we want to add our nitro group first. Which is a meta director. And because it's meta and I want my bromine meta, I can just add that right now. Then reduce my amine, or my nitro group to the amine anyway. All right, so after you do the amine there, we can use the HONO to make your azo compound. And then just add water to get to that phenol. Questions on that one? All right, how about this one? Ideas for this one? I feel like this one is deceivingly simple. But I don't think it's that simple. So if I look at or think about reactions, I want to add, this is my starting molecule in theory, and I need to add a carbon group, which makes me think of a Grignard reagent, but I don't think we can do a Grignard with a amide. And I don't see anything that we use it with an amide. So the nitrogen that is here in our starting material might not be one that we even want to use. So we might end up losing that because we can't do a direct Grignard with an amide. So I'm thinking maybe we make it into a nitrile. So if I make the nitrile and then add the 2 carbons via a Grignard with this, and an acid workup, that is going to give me a ketone with the 2 ethyl groups. And then now I can just do reductive amination with ammonia. So that nitrogen will take the place of this carbonyl and then get reduced. And if it helps to draw it this way, you can think of that as well. So that is how you would do that one. Questions there? And that was the last synthesis problem that I have for today. So if you have other questions, I'm happy to answer them. Otherwise, good luck on your quiz.